Welcome to the fifth video in the Day of Datomic training series. In this video, Stu Halloway turns to the Datomic view of time, which brings us right back to transactions and how to use the Datomic log API and filters to navigate through your data. Stu will also talk about how to use sync to correlate activity across multiple peers, and Stu closes things out by talking about how to permanently remove data from Datomic using excision.
Welcome back. Now is the time we've all been waiting for, literally. We're going to talk about Datomic's time model and how that sort of pops up in different ways when you're working. We're going to start by talking about reified transactions. So you've seen already that a Datomic datum has entity, attribute, value, transaction. So every Datomic entity refers to a transaction. That transaction itself is an entity. So when we say a reified transaction, what we're basically saying is a transaction is a thing. Right? It's a thing that you can actually look at and touch. Whereas in an update in place system, a transaction can be invisible. Right? It's just, it looked like this and then it looked like that. Well, what was the change? I don't know. Right? Some piece of magic that made that happen. Then we're going to talk about T. So I've said earlier that Datomic keeps a global ordering of time. That time is called T. And that's just a number that gets bigger over time in a system. And along with T, there's the notion of basis T. Basis T is the most recent T a particular database knows about. That's its basis. So you can walk up to a database and say, what's your basis T? And it can say 11,000. And you're like, oh, OK, I know about the history of the universe up to 11,000. Then we're going to talk about the log. The log is Datomic's primary initial storage of data. Right? As you put transactions into Datomic, it stores them in the log. But the log, therefore, is also an index indexed by T, which means that given a T associated with a transaction, you can go in the log in Datomic and say, what data happened in this transaction. So somebody in the earlier talk talking about the indexes said, what about a T leading index? Well, the log is a T leading index, but it's not built and maintained the same way the other ones are, as we'll see when we talk about the operational model of Datomic. Then we're going to talk about filters. The most important filters are probably the ones that Datomic gives you. So Datomic gives you as of, since, and history views of the database over and above just the ordinary view. And those are things that filter out things based on time. But you can also write your own filters. So you can write an arbitrary predicate and say, I'd like to filter the database based on this predicate, and then pass that filter database on to query or whatever else. Then we're going to talk about the problem of more than one peer in a system wanting to make sure that they are working with the same information. We already know that the system is consistent, which means that everybody's going to see things happen in the same order. But what if I'm aware of things up to time 11,000 and you're aware of things up to time 12,000? We both saw everything happen in the same order. I just haven't seen everything you saw yet. Right? That's a fundamental reality of physics. Right? If things are in more than one place in the universe, they see things happen in they may see these things happen in the same order, but they're still going to see them at different times. And then we're going to talk about violating flagrantly violating Datomic's time model, which is going back in time and making something unhappen, which is called excisions. So we will start with reified transactions. Transactions are entities like every other entity in the system. Every datum in the system, in addition to being associated with E, is associated with a transaction. Datomic assigns transactions and entity IDs as increasing numbers over time, and these are associated with an underlying number called T, which is just a global increasing counter per database. In addition, transactions are associated with a wall clock time, because you're not going to find 11,000 to be that interesting a number. At some point, you're going to say, well, when did that happen out in the world? And so there's going to be a wall clock time of, this morning at 9 a.m. and 31 seconds, and 0.001 milliseconds is when that happened. Transactions can also have additional attributes that you specify. So in addition to talking about your own entities in the system, you can talk about Datomic's transaction entities. And this gets used for things like data provenance. So you can say something like, this transaction was put in the system via the web interface. And that transaction was put in the system by an admin. And this transaction was put in the system as part of an error correction. So statements about the purpose of a transaction or the use of a transaction can also be made in the system. And transactions have their own index, which is called the log. So let's look at this from an API perspective. Given a particular database, you can walk up to that database and say, give me the basis T. So that's going to give you a number like 130.223. And what you know about that is all the t's before that are already in the database, and all the t's after that are not. Given that basis t, you can find out what the transaction entity is that goes with that. So t to tx, that's how you read that function called t arrow tx. That says, given a t, give me the tx associated with it. And notice that t to tx only takes the number as an argument. It doesn't take the database as an argument. It doesn't need the database. What does that mean about t and tx's? They have a mathematical relationship, right? It has nothing to do with the database. And what that is literally a tx is just a t plus the tx partition, right? It's those high bits that put something in the tx partition. So a transaction entity is just that. And then, given a transaction entity, you can pull from the database the instant in time where that happened. So here, I asked about a particular transaction, and I found out that it happened on, October 13th, 2014, blah, 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 at some particular time. So this is all information that you can reach in and fall out. Again, I should mention that at the bottom of most of these slides is links to code that do the same thing. We're going very fast today. So my hope is to give you all the high points of things you could try, and then give you the ability to go back and try them at a subsequent time. So as you're looking back through these slides, all of these links are live, and you should be able to click on them and go to the place in the code that does this, and then run the code and see for yourself. There's also a log. The log is not associated with a database value. It's associated with the connection. Right? It's an ongoing thing. It represents the connection's ongoing activity. And given a log, which you can get by calling d/log on a connection, you can then ask for a range of transactions with tx range. Tx range takes a log, a t, and a later t. And so if I want to ask for a single transaction, I would say, given a particular basis transaction, and then the increment of that basis transaction, that's going to give me a range that's only one big. Right? I'm going to go from 7 to 8. If I asked for a tx range that was longer than that, then the API is going to give me back a longer range of transactions. This is a very powerful API if you have something to do like a batch job every night at midnight. Like you want to go back and say, I want to process everything that happened in the database today. You go and find the point in the log that you finished processing the last time you ran the batch job. You pass that in as the first t, and then that last argument to tx range can be nil. Right? So that's a way to say, give me everything from now until the end of time, so far as the database knows. So if you have any kind of batch job that needs to depend on the database and then work with only the most recent stuff, you pick a time t and then say, give me that range. This log API is directly exposed visually to you when you're on the Transactions tab. So you can go and actually look at the individual transactions. They show up graphically, and then you can click on them and drill through. And that console, all it's doing under the covers, is calling tx range. And eventually, when you drill down to having a single transaction, then it's going to be calling tx range with just that one transaction, and then that transaction plus 1. Transactions can have their own attributes. So in the top transaction data here, I'm creating, this is back to our social media database. I'm creating a story whose title is codec and whose blog whose URL is whatever. And then I'm annotating not the story, but the transaction with a publish_at attribute. Publish_at is an attribute I made up. Right? I put it in the schema just like you would put any other attribute in the schema. But notice that the temp ID that I'm referring to there is db.parttx. All temp IDs in db.parttx unify to the transaction. So it's ridiculous to put a number in that call to temp ID. Right? I could say dtemp ID db.parttx -1 or -2. No matter how many different numbers I put in there, those all always unify to the transaction, which is assigned by the transactor. And then this lets me say additional things about the transaction. Here I'm saying that all the information in this particular transaction needs to be published at a certain time, where I said, right now, in this case. The other thing you could use that for, other than adding your own attributes, is you could also add the dbtx instant. Datomic will assign a dbtx instant based on the wall clock of the transactor. It'll say, hey, I'm doing this transaction. It's right now. Here's the tx instant. But if you set the dbtx instant, and notice that I'm setting it on an entity again in db_parttx, then you're overriding that. The only place you should probably do that is imports. Because what you're doing now is taking data out of another system that happened 5 years ago, and you want to make it look like it happened 5 years ago in Datomic. There is a rule about setting dbtx instant. And that rule is it has to move up over time. Right? Because when Datomic does it for you, it's using the clock on the transactor, so it's going to do that. This also means that if you do something ridiculously dumb, like setting a dbtx instant that's in the year 3000, you've now rendered your system unavailable. Because all further attempts to create transactions as of right now are going to say, oh, I think it's already the year 3000. I refuse to accept any data from the year 2014. So be very cautious with monkeying around with dbtx instant. This also means that you should be pretty disciplined about keeping your clock time on your transactor reasonably sensible. Right? It doesn't matter if it's 10 seconds off, right? But if it's 5 minutes off, then when you turn off that transactor and turn on a new one, that new one might not be able to transact data for 5 minutes until its clock gets to the point where the other transactors is. All of this stuff is, relatively deep voodoo. The easy stuff is using the filters. By default, if you just grab a database from a Datomic connection, you get the current state, what's true right now. If you call .asof on that database, it applies a filter that says, show me the state as of some point in the past, inclusive, right? Up to and including some point in time. If you say .since, then that says, give me the state since some point in the past, exclusive. So leave out everything up to and including some point in time. And if you say .history, it says, show me the sort of panopticon view of everything that ever happened, all overlaid with itself simultaneously. Now, a couple of sort of check your knowledge questions. What kind of argument would it make sense to pass to as of or since? Pass what? An instant would make sense. That would say, go and find the point in the database closest to that instant, resolve it to that t, and go. Or you could just pass a t, or you could pass a tx. Right? There's a t and a tx and an instant. So these APIs will take any one of these. Right? Another test your knowledge question. Of these 4 databases, one of these filters is incompatible with making entities. So if you call the Datomic entity API on that database, it's going to say, I can't do that, and throw an exception. Which one and why? History. Why can't history make entities? Well, history says I have an associative view. I have a key, and that key has a value. If I'm looking at the history database, which value do I assign to that value? What if there's more than one? Right? What if my name used to be Stu and now my name is Stupid? Or whatever. Right? How do I know which one to assign? So it doesn't make sense. And this goes back to the point that entity views don't know anything about time. And so the regular view and the as of view and the since view all have a cohesive notion of time, but the history database spans time. So you can't really do that. Now, just to make this specific, we'll go through a complete example. So this piece of data, and by the way, the program that runs to produce this data is this program linked at the bottom. So if you want to go and run this later, including the thing that prints out this table. So you can take this all the way through to making your own slides and doing your own Datomic presentation if you want to. So what we're seeing here is a store that is keeping track of its inventory of dilithium crystals. And the horizontal bars I added by hand just to show you the transaction boundaries. So the first transaction says we have an item called dilithium crystals, and there are 100 of them. The second transaction says how many dilithium crystals are there. Can you guys actually read that? I know it's a little 250, right? We go from 100 to 250 in the second transaction. Can everybody see that? When I walk in front of the screen, I get washed out, but it's that row, right, that sets us to 250. Let me take the time now to point out one other thing, too. The item count here is a cardinality 1 attribute. When I set the item count to 250, I do not have to retract the 100. Datomic makes those retractions for you. So in all probability, we can't tell by looking here, but in all probability, I didn't explicitly say retract 100. I just said the value is now 250. And Datomic says, well, the value used to be 100, so I'm going to retract that and then add the 250. The third transaction does what? Let somebody else tell me. Retracts 250 and sets it to 50. The fourth transaction retracts 50 and sets the count to 9,999. Now, one of the things that's subtle about this one is that it also has a TX error on it. So somebody annotated this transaction to say that this transaction was made in error. And in fact, the example is less than entirely perfect because this annotation could have been made maybe later in time, in which case it wouldn't show up in this transaction. It's a little bit silly to annotate it as an error at the time I'm making it. If I knew that, why would I do that? So shame on me for the example. I'll fix that. And then finally, the correcting transaction, presumably, sets it from 9,999 to 100. Given that Datomic keeps this information, it's possible for you to find out the past, obviously. It's possible for you to make corrections without forgetting that you had bad information, which is super valuable in a real system, right? Because if you have bad information and then you correct it and the record of that correction is completely lost, and then someone calls you from one of your partners and said, your system did this to us yesterday and we're trying to track it down, you're like, well, I don't know. Right? So being able to do something like annotate a transaction and say this is an error correction as opposed to just sort of quietly losing data. Now, given this is the actual raw datums, when you're in a normal operating scenario, you're looking at the database with all the old data filtered out. So you'd have all those guys are filtered out. Right? Those are all matching assertion and retraction pairs. Assert 100, retract 100, assert 250, retract 250, assert 50, retract 50, assert 999, retract 9,999, and then you're left with, this is the only visible value for item count. So that filtering goes on in the database for you automatically, normally. If you're using an as-of filter, then everything past a certain point of time is filtered out. So time goes down on this slide, roughly. So you'll see that it turns into a graph like this is all gone, and the value as of a particular point in time is 250. And notice it still filters out values older than that. So this is how you teleport back to the time when the count was 250. If you have a sense filter, that's the opposite. Right? Now you have a bunch of old information is missing, and then you still have assertions and retractions canceling each other out, and you see that the count is 100. It is very tricky to use the sense database. Because the first mistake, first off, you almost never need to use this. Secondly, it's there for sort of symmetry and completeness. Secondly, the first thing people do when they use the sense database is they're like, OK, I'm going to go look up the dilithium crystals in the sense database and then see what their count was in the sense database. But you can't look them up because the unique identity attributes that you'd use to look them up is where? Back in the past when it was created. So if you actually want to look them up by their unique ID, and then ask a sense question, you actually need to look them up against the ordinary database and then ask the sense question. So you have to have two different databases. You can do this. You can write a query that does a multi-database join. Right? You can pass in the same database argument twice with two different filters passed into the same query. So you can do that, but it's much more likely if you're doing something that's this time-oriented that you'll just say, oh, the heck with it. I'm going to use the history view. And the history view just sees everything. Right? And then you can write your own program that consumes these and asks the question you want to ask. So now I'll tell my story about the book club again. So you're in a book club, and you're all ordinary readers of books, which means that you're consistent readers in the acid sense. You read chapter 1, then you read chapter 2, then you read chapter 3, then you read chapter 4, and so on. And the problem is that we all plan to get together and talk about the book, but Gary wants to talk about chapter 11, and I'm only up to chapter 7. So I'm not happy with that outcome because I don't want to have things spoiled for me. And the analogy to that in a distributed system is the transactor is sending out always ordered stream of changes to every peer in the system. So peer B is receiving 40, then 41, then 42, then 43, then 44. Peer A is a little bit ahead, right? It already received 40 and 41. It's receiving 42 right now. From a single peer's perspective, this doesn't really matter. But imagine that a web request comes in from the web tier, and the load balancer sends it to peer A. And peer A has just processed 42, so it gives back the user an answer based on time 42. That user then goes back through the load balancer, goes back to the web tier. The web tier comes back in and asks a question about that data, But the load balancer now is not sticky, so it routes it to a different web server, peer B. Peer B hasn't heard about 42 yet. Oops. So that might not be great. Now, first off, this is a very narrow window because the transactor's connections to the peers is substantially faster and less latent than the peers' connections through the web tier and blah, blah, blah. So to actually physically construct a scenario where this happens is a little bit challenging, although we have had a couple of users manage to do it. And so what you can do in this situation is you can call sync. Given a database connection, you can say sync 42. That will give you back a future that will be completed, a Java future, that will be completed when 42 is reached. And that's the only time you need to do this is when you're correlating activity across multiple peers and making sure you're working at the same point in time. And in fact, if you were going to be particularly cautious about it, you could use sync followed by as of. Right? Sync to 42, make sure I have up to 42. As of 42, make sure I'm not looking past 42, even though I might know, more than 42 right now. Again, this is a fairly advanced scenario. We did have an interesting use case from a user recently where you end up wanting to do this. And that's when you have a transactor function whose job is to ensure the system is in some state. And then the peers want to make sure that they know about that state. So they want to make sure that that transaction function has run. They need to sync to some point in time t, to make sure that that thing is run. So it's definitely useful, but kind of an advanced case in most applications. In fact, I would say that 90%, if not 95%, of Datomic applications in production never call this API. And then, and I'm not even going to show you how to do this, right? Right? There is a technique in Datomic to permanently unrecoverably lose data. To take this data and say, pretend like it never happened, make it magically vanish from the system. This is ugly. It is very hostile to performance because it requires Datomic to do complete rewrites of indexes to do. So it can cause problems that way. And the only reason you should do this is if you are given some sort of legal takedown notice where you're told this data has to be removed to comply with privacy laws or there's a lawsuit or whatever. That's what this is for. That's why the feature is there in the system. Datomic does have an interesting characteristic here, which is that the fact of an excision is recorded in the system permanently, and that can't be excised. Right? Obviously, if you record what you forgot, you didn't really forget it. Right? So there's a little bit of a sort of tricky circular thing here. But you can say, at this time I forgot something, which might be necessary from a liability perspective. Right? You might say, at this time I forgot some values of this attribute. I don't know what values they were. I don't know what entity they were associated with because I was told to forget that. But if somebody comes back and says later, your system's not performing as expected because it should have values for this attribute, you can say, well, maybe my system's broken, or maybe I was forced to remove stuff at this point in time, and there's a record of that in the system. It's another example. It's amazing how even forgetting gets better in an immutable system. I'm not saying this is great because it's a miserable situation to be in, but when you're in this situation, that's what you end up needing. So, for the next lab, what we're going to do is you can explore your own data. This includes the data that you've created earlier in the class for yourself or the MusicBrainz data set in the console. The console has the time filters as checkboxes across the top. So you can check as of and choose a calendar, or check with, or choose the history database. Then I'd like for you to go out to the REPL and try querying against an as of DB. And in these cases, you can actually run directly through these examples that are in the tutorials in the Day of Datomic example, and then use the log to recover a recent transaction, and then annotate a transaction to provide information about a transaction that you can come back to later. So we will return after the lab break, and we will pick up with our final session, which is investigating the operational characteristics of Datomic. Any questions before we break for the lab?